Now we come to compaction. This is a topic that sometimes gets into basic soil mechanics courses, and sometimes it doesn't. And I think that's unfortunate. And it's almost inevitably, however, one place that you inevitably see it is the lab. I think it's unfortunate that it's not covered. And a lot of the stuff, just for my own students' benefit, that you'll see here will be stuff you need in the lab. And a lot of it is a general overview of compaction. Compaction, we're talking, once we find out what kind of soils we have in the ground, sometimes it's necessary to make some changes. One of the ways you make is so-called soil improvement. And there are many ways of improving the soil, and compaction is probably the oldest and best known of those. By the way, for my students, those photos of the Cracker Barrel in Cleveland, Tennessee, when they were building the Douglas Inn in front of it. So, with that in mind, and you'll see the significance of the sheep's foot roller you're looking at in just a few minutes. Let's start with relating earthwork and compaction, because the two are very intimately related, and usually they're done together. It's very seldom that you would actually move earth around for any reason without somewhere along the way compacting it. The citation, my biblical citation here, what this is referring to is fill and grade work. And it's been going on a long, long, long time. It was common in the ancient world. It was how the Romans built their own straight paths and their own straight roads. And it's how everybody else has done them ever since. So fill and grade work goes back a long way, and it's an important part of civil engineering, and has been from the beginning. Overview of earthwork and compaction is to change the ground surface from some initial configuration to a final configuration, so we can put a road or railroads, or landing field of aircraft or whatever. The final configuration is generally defined by a grading plan, and it must not create slope stability problems, either temporary or permanent. That was the Swedes' problem with their railways, which got them to the slope stability more deeply. And fills must have sufficient strength to support their own weight and external load. They have to do their own, they have to keep themselves up and whatever we put on top of them. They must be sufficiently stiff to have more settlement, to get rid of settlement problems, even whether they're in the wet or in the dry. For the cores of earth stands must have enough conductivity low enough to restrict the flow of water. Tunneling under dams and that kind of thing has been a major problem with dam construction and operation. For bases of pavements, they have hydraulic high enough to enable drainage of the roadway. I talked about that the last time. And they should not be in cold climates susceptible to frost heave, whereas when you freeze water, it expands. Ice has lower density than the water itself. And that's the expansion of the water in the soil is referred, when it comes together soil, is referred to as heave, frost heave. Historically, large moving were possible in ancient times, as the verses definitely suggest, but it took a great deal of labor and time to execute most of those. The Romans, and frequently sometimes compaction, would actually have large logs, and they would have handles on them, and people would pick them up and drop them to do compaction. The thing that changed construction in general and earth moving in particular was the advent of steam construction. And that's close to home because I have been involved many years in a piece of equipment that still could be, usually run off of air now, but was originally designed to run off of steam for many years. For example, the original Panama Canal project involved the movement of 75 million cubic meters of earth. That's a lot. That's still a lot of earth. It was And there were all kinds of ways of getting around this problem. One, to actually be able to dig up, move, put down, and compact stuff is decently labor intensive. And one way of getting around this problem was hydraulic fills. Basically, you took a lot of soil, you mixed it up with water, you conveyed it to another part of the site, and you put it there. The problem was that ensured that the fill at the other end was unstable, and in fact created a major disaster in 1938 at the Fort Peck Dam in Montana. And after that, hydraulic, civil engineers and the people who were actually writing checks for the work decided we had all the fun we could stand with it, and that's pretty much gone by the wayside. By the way, however, that illustrates something else. Inadequate compaction is one of the major reasons why we see failure in particularly in transportation-related structures, but civil structures in general from a geotechnical standpoint. If you need something to be compacted and it's not compacted properly, it's going to settle further, and bad things are going to happen. The advances in earth-moving equipment, however, have pretty much removed the need for, having hydraulic, for doing this kind of thing. So we've moved on. Earth-moving equipment, basically the tractor or crawler, and was the thing that really made earth-moving equipment practical was the development of the tractor, the crawler. In the early 20th century for agricultural. Later it was adapted for the tanks. The first tanks in World War I were actually were mostly on Caterpillar track, at least the ones that had anything to do with the United States did. All the early tractors were track-mounted. Track-mounted is very powerful, but it's slow. In some applications, you have to go with a track-mounted piece of equipment, particularly with their soils are poor, and speed is not the number one issue. You can also there's also wheel-mounted track are available with tires, but they're not as suited for the rough terrain. When you get down to the really hard terrain, your tractors are much more versatile in terms of what they'll do. Generally speaking, a lot of construction equipment is done this way. It's based on a modular concept, and it starts with a tractor base, and you add different attachments to it. Contractors like to get as much out of a piece of equipment as they can, and so they like equipment that is versatile. The bulldozer is the most common, and you can obviously change the blade if you need to for different soils, different applications. Another tractor or crawler is our excavators, as you see there. Or you've got loaders. Loaders vary a little bit in that they're able to pick up the load and move it. An excavator is probably one of the most versatile pieces of equipment that you have on a job site. They can do, obviously what they're called excavation. They can do other types of work. I've been involved for the last several years in actually mounting pile driving equipment on an excavator using a mast, which is an interesting combination of civil engineering, structural and geotechnical engineering, which is typical with pile driving equipment. But most of the work on the mast itself has been structural. So it's a very versatile piece of equipment, and the more, again, it's like the more you can do with one, the better. You also have you can put other attachments on. You see a lot of attachments in excavators, tamping attachments. That is for lifting and detail clearing, like trees and brush and that kind of thing. You can also put vibrating, to get vibrators to get tree stumps out, that kind of thing. Conventional earthwork starts with cleaning and grubbing. Usually you don't want to try to do a lot of earthwork when you've got a lot of overbrush. and then you strip the either remove and store the topsoil, or you can also sell it to somebody else. Unfortunately, that's the way a lot of development is done, where they actually sell the topsoil, and then you try to grow something and the house is built on it, and you're going to have to put sod back to it. And of course, oversized items are something that you have to deal with in excavation. Excavation, most of that takes place at the construction site, and you have to actually have the provision to move, particularly if you have to move the excavated stuff off-site. Sometimes you're able to move stuff around, and at one time, in fact, we talked about cut and fill calculations in this course. I don't do it there. I do it. I mentioned cut and fill. I want to make mention of something else while I'm coming really quick. A few years back, about 20 years ago actually, I was asked to become a co-author of this, which is Soils in Construction. And it's a textbook that is really basic geotech for contractors and engineering management people. And so that's why I don't use it in this course, but there's the part of compaction includes the fill and grade type of thing, and also a lot of compaction information, which was part of the expertise of my co-author, and actually the original author of the book, Lee Schroeder, who was head of the Civil Engineering Department of Oregon State for many years, very much involved also in cellular cofferdam design, and at one point he was interim athletic director at Oregon State. So you never know what jobs you're going to get when you get into academia. So anyway, my hat's off to him for all the good information he's put in here on that and many other subjects over the years. One of the fun things, and we see this in this area quite a bit, is excavation of rock. Now, soil is one thing, but rock is entirely different. We normally rip rock, and we talked early in the course about the direction, the direction of the bedding planes versus ripability, we can use blasting sometimes. Blasting is very much of a last resort because of the effects it has on the stuff around it. This is a quick chart showing different the fracture spacing of the rock and the point load strength of it, and what you do, how you would get it out. Either anywhere from just digging it up to blast a fracture in very difficult rocks. Another useful chart is, and this is an interesting. When we talked about seismic methods, we talked about the velocity, the sonic velocity, the longitudinal velocity, sonic velocity of the material. That can be used to help us determine what type of equipment we need to get rocks out as well. And this is a chart, and there are other charts very similar to that, which give us that type of relationship. There are different types of things, and I'm not going to spend a lot of detail. Again, if you're interested in many of these topics in terms of the contracting and whatnot, Soils in Construction has quite a bit of this information as well, and you can get it elsewhere. There are, once you get it out, many times you will move it and place it. A lot of times we take it to a dump area or whatnot, but ideally we like to reuse whatever we take out, either on the site or somewhere else. We just don't like to just dump it and leave it if we don't have to. We can, for example, some rock can end up being aggregate used for making concrete, for example. And so this is sort of a brief overview of earthwork, and I don't want to spend a lot of time on it, but it's to give you an idea of something that looks as simple and has been going on as long as as fill and grade work has been going on, has a lot of complexities to it. Now we come to the overview of compaction. The compaction, by definition, is the densification of soil by removal of air and the rearrangement and reorientation of the particles. And the object is to increase the load-bearing capacity of the soil and reduce settlement, which are not exactly the same. They are related, though, but they're not exactly the same. And I would say that the settlement issue is probably the more important of the two. This is the first time we talk about, and really, pavement is a shallow foundation, and we're starting with shallow foundations. The number one reason why shallow foundations do not perform the way they're supposed to is excessive settlement. And obviously, inadequate compaction can lead to excessive settlement. You get some compaction just driving over the site, but it's usually not enough. Basic procedure is very simple. Soil arrives on site. It has to be laid out in lifts. And lift basically is the amount of the depth of the soil between, we start with a grade. The lift is the first round of soil. We put it there, and then we compact that. We put another lift on there, and we compact that. Then we put it's just sort of a layered process. And the lifts are what we call those, are how we refer to those layers. You have to moisture condition them and compact, and then you put the next lift on. There are reasons why. The reason why we cannot do it all in one shot is that if we're compacting it from the surface, and one way or the other we're compacting it from the surface, any method we pick, once we realize it's suitable for the soil, any method we pick is going to have a limitation in how deep it's effective. And I think we kind of understand that in our mind. So you don't want your lifts to be thicker than the depth of effect of the compacted method you've picked. And there are several methods of which we do that to actually compact. We can do it by pressure. We can do it by impact. We can do it by vibration. And by manipulating it as well. And those are the four basic ways that we compact soils with. These are an overview of different types of compaction and what kind of equipment we might use, how deep it can go. You see first the equipment type. The second is applicability. The reason why, for example, in the area around UTC, you see so many sheep's foot rollers is that they are primarily intended for cohesive soils, fine-grained soils, and that's pretty much what we've got around here. Lift thickness is 6 inches, and you make several passes. In other words, how many passes? You've got a lift thickness, and then you got the number of passes: 1, 2, 3. You go pass over several times, and there are other types of rollers, rubber tire rollers, and smooth wheel rollers, which are usually safe to last, and vibratory equipment. I'll talk about that in a minute. Or tamping, where actually just bait on the thing. And I'll let you look at that and see what, it's about as nice a summary as I've ever seen of matching different types of equipment to the soils, because generally speaking, one thing you really don't want to do is to have to haul in a bunch of soils to do compact. You try to use the soils you have there to use compaction. Sometimes you have to move it around, but still you want to make that distance of haul as short as possible, and so you're going to want to use a soil from somewhere around it, which is why, generally speaking, in most areas you have 1 or 2 methods of compaction that are suitable, and that's pretty much what everybody uses. The sheep's foot roller is an interesting development started in Los Angeles, and a contractor was having trouble doing his roadway compaction, and a flock of sheep beat their little hooves across one, and he comes out and he realizes his compaction is pretty good, and he says, hey, but the good news is that the sheep have done my work for me. The bad news is I can't count on them showing up again when I need them. So he develops the sheep's foot roller, where basically you've got the drum and you've got these feet that stick out of it to simulate the work of the sheep. It's a combination of tamping and kneading with a little vibration in there to do your compaction, and the pressures can vary. 100 to 500 psi, and compact layers the order of 6 inches and 4 to 6 passes. And again, it's mostly for fine soils, which is why you see them around here. Pneumatic tire and vibratory rollers. Pneumatic tire rollers are due by kneading, and they usually have a weight box for additional compression. And they're useful in a wide variety of soils. Vibratory compactors basically are use an eccentric weight or weights, usually more, one or more than one, to actually have an alternating sinusoidal force on the soil. I'm currently have some involvement in some projects I've had a dialogue is more accurate with some my colleagues in Europe on this particular topic. It's related to the work on vibratory hammers, which I feature prominently on some of my websites, and you can see that. We'll talk about that later. It's an interesting method of compaction, and it's usually they're used in granular soils, but they can also be used in other ones. We frequently talk about smooth drum rollers, and there's a lot of misconceptions about them. The first one is that they're called steamrollers. Well, we haven't powered them with steam in a long, long time. So steamrollers really kind of a misnomer. They're not really good for, really deep compaction. They're only good for very shallow, and they're usually used to finish, particularly in paving work, to finish off a roadbed so that it will be smooth and make it easier to work on it and pave over it and all this good stuff. So we also have impact rollers, where you have those big triangular things you see over there. Here actually have the make impact, and impact can be used, and we'll see another method of impact compaction here shortly. And it can be, the thing about impact compaction, it can compact soils to a very significant depth. And then we have soil. This is a nice little chart that shows what different soil classifications and compaction requirements. Again, instead of, with compaction, we try not to have to replace if we do replace soils and move them around, but if you've got local soils which are abundant, you need to learn how to compact them properly. After that, you have an earthwork, where you smooth things out after the smooth rollers, and before you start putting anything on top of it, whether it be a foundation, a pavement, or whatever. Now we come to the Proctor compaction test. How do we test? One of the things about soil mechanics particularly is that we don't like to fly blind with stuff. We like to test and verify. Theoretical stuff is nice and whatnot, but we really need to have verification. Basically, Proctor was the city engineer for Los Angeles, the home of the sheep's foot roller, and he came up with this method. I'm thinking it's been about 100 years ago. he came up with a compaction test to do this. Basically, what we're trying to do in the Proctor compaction test, compaction is done over a large area. What we're trying to do is to take a large area and replicate it in a small place, and to be able to use that to estimate compactive effort and the effect it has on the soil. Now, I'm going to show you something that, generally speaking, soils around this area, being cohesive, will generally form a nice curve like that, and you'll see at the top this is the classic dry unit weight on this. You're going to see this until you're tired of it. Compaction moisture content in this one, and we run this series of Proctor tests, and we get this. With our type of soils, we'll get this type of thing. With sands, it's a little different. It's quite a bit different, actually. If we were to run it with a certain, and we're going to talk about a certain weight, we use, but we have a selection of weights and a selection of compactive efforts. And we can run different weight, different compactive, we'll get that. And we're talking, and if we can do this with different types of compactive efforts, we can draw this nice line of optimums, where we can use that on the job site to pick proper equipment and lift thicknesses for our compaction. Line of optimum teaching is something, again, that I feature in Soils and Construction, and it's not a particularly well-covered topic in most geotech textbooks. But let's go on and see what the Proctor compaction test is all about. Metal molds, cylindrical molds, you've got three things. You have the base plate, you have where the soil is basically placed, and this is the ring on the top. And over it, you've got a rammer on the side, which is basically a tube, and this shows you the inside of it. It has a rammer at the bottom and a handle at the top, which you lift up and drop. Traditionally, there are two compactive, there are two basic tests. The standard test has the mold has the diameter of 4 inches, and the soil height is 4 5/8. That's 1/30 of a cubic foot, or I think it's the 0.009 cubic meters, which we talked about earlier. The tamper is a 5.5 weight, drop of 12 inches, kind of like the SPT. And the layers, we do it in 3 lifts. Basically, when we do the compaction test, we put maybe we want a third up at the end. We put 40% or something like that. Depending, and there's a lot of experience involved in that. And then you take the tamper and you lift up and drop it a certain number of times. 25 is the general number, and then you tamp that down, you get that down, you put another third in, and then you do the same thing. You go around, make sure when you're doing this that you get the whole area evenly of energy. And then you put the last third in, you beat it down, and you're done. The modified, the difference between the modified is done in more lifts. That uses basically the same mold, but, and this is an important thing, the weight is heavier, the drop is higher. You go for 10 times 18 inch drop, and you put more lifts. If you were to take the energy of the drop, multiply it by 25, you get the total energy you've put into a layer, and then turn around and divide by the volume of the layer, you get the compactive effort. For a standard Proctor, that is 12.375 foot kips per cubic foot, but for the modified, where you get thinner layers and heavier, more energy into it, you get 56.25. So that's the difference between the layer. And you can mix, these are the basic two. You can mix or match your you can do some mixing and matching to change the compactive effort between those. But that's basically the idea behind this line of optimum. Say we ran that as a standard and that with a modified, and we can get an idea. If we did a couple more between those, this line of optimums tells us what compactive effort we should be trying to shoot for in terms of our actual compaction. And this is that in pictorial form. To prepare a sample, you start with a number 4 sieve. There are special procedures if you've got a lot of very large gravel or large material in it. You use a number 4-inch mold, which we talk about 20 pounds of material required. For if you have gravel samples, that's one of the special procedures. Use a bigger mold for gravel samples. Samples should be air dried, just to get them dry. And then addition of water. What you have to do is kind of like the Atterberg limit in this respect. You have each sample. You add it, and to do it by Hoyle, you use a different for each compactive cycle. In other words, each set of 3 or 5 lifts and beatings and whatnot. You act like to do it according to Hoyle. You have to take a you add a different. You use a fresh sample. That's why you have 20 pounds of material. You would use different. Same you would use different set of material for each, and you would add different water content to each, kind of like you do with the Atterberg limits, and you will construct that. And they will show you how to do that in just a minute. Then you take the specified moral, about 40% full for the first lift, and this is standard. Obviously with the modified. You would have 5 lifts. You would probably say, 20%, maybe 30%, maybe 25, 30, depending on the soil. And then you would do it a third of the way. And then once you're done, you'll probably, hopefully, you will have at the very top of the, you'll take the top ring off, and there'll be a little soil over the top. So you trim the specimen off, and then once you get that, you essentially get that, and then you remove a little of the moisture. You don't want a moisture content the whole enchilada. You want to take a little bit out of it, your normal, and then you run the water content test like you do any other water content test, and then you'll do that again with a sample of a different water content. You run that, and then that, and what you'll end up with, and I know this is a series of and they'll plot the water content of each sample against the maximum dry density of each specimen, or dry unit weight, depending whether you're in kilonewtons, whether you're dry density or dry unit weight, depending on the units. We talked about units a long time ago, so we won't do that again. Now, and you'll get a curve. And most cohesive soil guards have curves look like this. Now, there's one thing you got to watch for. There's a thing over here we call the zero air voids curve. And the water content, and basically that assumes that the zero air void point is the point at which for a given water content and dry unit weight, the sanitary sap weight. If your curve ends up on this side of the zero air voids curve, you have done something wrong. Either in procedure or in calculation or in data taking. Well, it's physically impossible, so either your data you've taken is bad or the calculations you've done are bad. So that's not, I mean, once you get past 100% saturated, that's it. Let's look at an example. Compaction example. And this compaction example, there are two ways you can get a compaction problem. In the lab, this is the way it's going to look. In your lecture course, we can usually, most lecture-related problems will dispense with the tearway. You remember with a water content test, you start out by measuring the weight of the tear, or the little can that you put the soil sample in. Then you put the soil sample in and you weigh them together. Then you put the soil sample in the oven, and here at UTC we use a conventional oven. It's possible to do it in the microwave, but it takes a little more skill not to screw the sample up. And then you turn around and you take the thing out and you measure the weight again. And so you take the weight out and then you measure the can, and then the difference between the two is the weight of the water. You can compute the water content, but you have to take the tearway out in both cases. So therefore, we've got 5 data points with these little water samples taken out. And we're going to say, so say for example, and I actually use for point 1. I'm going to use this point right here. We'll use that as an example. The wet unit weight of the soil in the mold, if you have a known, you see the mold is completely full of soil. It's better to be completely full of soil. That's one reason why you have to smooth it off at the top and make it real nice. The wet unit weight of the soil, you've weighed the mold. It's a tear too. It's a tear as well. In fact, that was part of the given in the problem. So I take the wet weight of the soil, I subtract that from the tear, and then I divide, and then I do a few, add gravity so I could get a unit weight rather than a density. You could do this with density, and you divide it by the volume of the mold, which is 0.009, and then there's actually 0.0944, and I end up with a unit with a wet unit weight of the soil of 17.98 kilograms per cubic meter. I can, if I know volume and I know the weight, I can compute the density. Second, water content. I do the same thing. I start with the sample. I subtract the tear. Well, actually start with the I take the tear out of it, and therefore I end up with a water content of 4.51%. The dry unit weight of the soil in the mold is basically by starting with a wet unit weight over 1 plus the water content, and you get 17.21. That's how I get that dry unit weight, is by taking the wet unit weight and then computing the water from the big sample and compute the water content from the little. Don't forget to, before you dig the little sample out, to weigh your mold after you've compacted it. That keeps you from having to go into the mess of drying the whole sample, all that soil, almost, in this case it's almost 1.5 kilos, 2 kilos of soil. That takes a long time. It's a time saver. So therefore, if I went through that, and if I did it again for every soil sample, repeat, lather, rinse, repeat, it's the same procedure, I will end up with a water, with a mass of the compacted soil mold, mass of the can, with all that stuff, which I had before, and I put those calculated out, and then I plot them. Now here's where things get fun. and I don't know why they have to get so fun with this, but many times students will plot this on a spreadsheet, and it'll look okay, but then they will do several. The biggest mistake you see, they'll try to use they'll try to go through a trend line plot, and I discussed the whole issue of trend line plots in my fluid mechanics lab. They'll go through that, and what will happen to them is that they will miss what they're looking for at this point right here. You need to plot a reasonable looking thing, and sometimes your results will make that difficult, but you need to try to get a reasonable looking curve over here, and these results are nice. So you could use an interpolative curve. You may have to use a trend line for knots, but whatever method you use, don't miss this peak. Sometimes you'll hit this peak with one of these data points. Not very often, but sometimes. And then you'll need to know this gives you 19 kilonewtons per cubic meter, your maximum compaction, at a moisture content of 11.8%. And that's the result you're looking for in compaction. Different soils have different effects depending upon the type of soil. I've mentioned that other soils don't, respond the way that the silts and the clays we have around here do. And then the compactive effort, you see the difference between the modified and standard. And this is another example of the line of optimums. This actually shows a line of optimums developed by playing some, by mixing and matching hammers and molds and whatnot to get different compactive efforts. So, that's pretty much, they could, you can do that and get a line of optimums. That makes it easy, fairly simple, and that's another thing that's explaining soils and construction better than I will here. But that makes it easy to develop a compaction spec. If you know what, if you only run one type of compaction, you've got one compactive effort and one result. If you run a series of them, you have several compactive efforts and several results. One of the things you do not want to do with lifts is make them too thick, or otherwise you will start having problems with the areas at the bottom of the lift, and you will get inadequate compaction. So you want to make sure that you keep your lift depth within the limits of the equipment you're using. These are some typical properties of compacted soils that we see. Relative compaction and relative density. There are two, these are two different things. Relative compaction, we get a maximum dry density and optimal water content. We think, well, we'll just send the contractor out there and he or she will achieve this and we'll all live happily ever after. And usually what you'll be greeted with, if you ever tried that, was laughter. Because soils vary, rain shows up and screws things up, all kinds of things can happen. So what we want is a compaction is a compactive effort that is reasonable, is achievable. So what we do is we call relative compaction. And what we do there is we say that, okay, we know you're not perfect. And if you're certain types of people will also include, we won't let you forget it. But it's going to be nice about it. So we'll let you achieve within a certain percentage of total. 100% relative means you got to hit the mark. Say 95 means you can get within 95% of the dry unit weight you're shooting for. That's all that means. That's the only thing about relative compaction. It's a fairly simple, and it's very important that you pick a relative compaction that get you the results you want in terms of the bearing capacity of the soil, but it is achievable for the soils you've got. And that's where design meets reality, so to speak. Relative compaction and relative density. Relative compaction can be used, particularly this is mostly with sandy soils, and we they can we can actually relate the relative compaction to the relative to the relative density that we want. So relative compaction example is this. Results from the previous problem. We got those results which you saw. We have a relative compaction of 95%. Find the maximum dry density and an equivalent relative density using the standard Proctor test. That's what we're trying to do to relate the two. And the easiest way to show that is an example. So the solution, the gamma target is pretty simple. You just take 19 multiplied by 0.95, 95%, you get 18.1 kilograms per cubic meter. That's the density that you really want. The relative density that you really are going to, the equivalent relative density is simply you take 95 minus 85 using the formulas I gave you. These formulas back here for if you use the standard Proctor test, and you end up with a relative density of 50. That's your equivalent relative density. Now we come into verification. Like I said, we don't like in geotech engineering to do things without proper verification. And that's certainly true with compaction. There are two basic methods we use. The most popular are the sand cone and the nuclear density test. Now, a little history, UTC history behind that I'll go into. Back about 20 years ago, when we were, we didn't have a soils lab until I think it was 2005. And we were preparing for a new building, which is now the EMCS or ECS. And myself and Dr. Owino, our department head, went to Knoxville to look at their labs up at the University of Tennessee at Knoxville. And one of the things that they had was a nuclear density gauge. They told us, one of the things that Knoxville informed us is that nuclear density gauge is the way that, generally speaking, in the most of the time, actual field uses to do it, which by shooting nuclear material into the soil and getting an estimate of the density. The problem is it's a regulatory nightmare. For one, that's one problem with in other words, if you get a nuclear density, if you or your company or your agency gets a nuclear density gauge, you better be prepared to justify the regulatory mesh you have to get into by using it a lot. My opinion at the time was, I don't think we're going to do this. So when we finally did get to the point in the lab where we actually started doing this type of test, we opted for the sand cone. Now the sand cone is the traditional way, and it takes time because you have to do moisture content test on it. But sand cone, any experienced geotech will tell you that the sand cone is still the reference standard for running this thing. And the sand cone is fairly simple. You take you take this apparatus, which is basically a bottle full of sand of known unit weight, and then you put it over this. Below this, you dig a hole in the ground. And through a very set procedure, you find out basically, if you know the volume of the sand that goes into that hole, then you know the volume of the hole, and then you can measure the weight of the soil you took out of the hole, and then you have the unit weight, and then you can dry it, and you get the dry unit weight and see if you've hit your compaction spec. That's the sand cone. It's a little time consuming, but it's still and there are some soils that still don't do well with nuclear density. So the sand cone is not completely out, and it's also another way of illustrating unit weight concepts in soil mechanics. And I'm not going to go into a lot of detail other than to say, first of all, you can have the use of check mold points to estimate your maximum dry density. You obviously check them in the lab and in the field and see if they line up. And also, this is a data sheet for the sand cone test as well. Vibroflotation. Now, we've gone through the verification. Let's look at some other types of compaction. Vibroflotation uses a special type of probe, and it's for deeper compaction. There's an eccentric weight that rotates around like this and creates a force like that. And usually they're jetted into the ground with water, and they can be done in a grid pattern. And we're going to talk about grid patterns later when we talk about consolidation. When a grid pattern in the ground, and you're able to do deep compaction of soils without having to take them out and then compact them back with lifts. Lifts assume that you can move the soil in, whereas with vibroflotation and other types of deep compaction, you can use what you've got. Other types, there's other deep probe type of compaction as well, other than just vibroflotation. And there's dynamic compaction. The French came up with this. Basically, all it is a large crane with a long boom, lifts a weight, and then lets it go, and it drops. And it's very crude. It's not a very sophisticated method, but you can actually, with that kind of drop, densify loose soils up to 5 to 10 meters deep, which is seriously deep. You see it more often. I say the nice thing about it doesn't take specialized equipment, and it doesn't. It just takes a lot of lifting and dropping and patience, but you can get very deep compaction, and an estimate of the depth of that can be done with this formula. So that concludes an overview of compaction. It's a very brief overview. I know it's going on for a fair amount of time, but it's an important topic that doesn't always get covered well in soil mechanics, and definitely will be a good preparation for doing it in the lab. So until next time, thanks for watching, and God bless.